What is the synthesis?
Basically, you put this special, so it's just an electrode, and you put this special rubber on it. It's pressure sensitive, so when it starts slipping against the electrode, it generates. Really? Or sorry, it doesn't generate a voltage. It becomes conductive.
Oh.
So then we're sticking volt. We have a voltage.
As it shears?
Yeah, as it shears. And you have a voltage. You put a voltage across it. You just have like another resistor, so it's voltage by the initial output. Yeah. Well.
Hey, Jacob.
Hello. How's it going?
Good. How are you?
Good.
Can you somehow mute yourself? We can hear your guys' conversation.
Oh, sorry.
All right, we'll get started here. So this is a Q&A and a brief presentation for the CAN-SBX 2019 flight campaign. As anyone listening probably already knows, so this is a program that we've developed in conjunction with the CSA, and they've so gracefully or graciously allowed us to piggyback on the gondolas that they and CAN-S are using for their own experiments. This is the second year that we're doing it, and so we decided it'd be a good idea to have a Q&A before the proposals are due, just to clarify anything and get everyone in the best position to make a good proposal. So I think the CSA has a brief presentation on their Stratos campaign, so I'd like to hand it over to them so they can give you a brief outline of that.
Excellent. Well, hello everyone. I'm Philippe Vincent, the payload manager for the Stratos program, and I'm here with some of my colleagues. Sébastien Lafrance, who's the mission manager for Stratos, is here as well, so we'll share the presentation. So let's start.
Let's start.
Okay, so first, key contacts for the SEDS challenge. It's Robert from SEDS-Canada and myself, Philippe Vincent, from the Canadian Space Agency. So if you have questions, you can write to Robert. If you write directly to me, I'll write him back your question, so he's aware of everything that's going on with the challenge. So let's start the presentation. Well, I'll continue with that one. So yeah, for the second edition, the Canadian Stratospheric Balloon Experiment Design Challenge will be in Timmins, Ontario for a second year. We got a campaign last year, and we're doing another one this coming fall. So let's start with an overview of our program.
Okay, now it's my turn. For stratospheric balloon flights, it started, well, that was a bit more than 10 years ago, where we had a request from the scientific community to bring back ballooning in Canada. And at one point, there was some discussion with CNES, and we realized that they had an issue where these payloads that they're flying will eventually fall back on the ground, and it wasn't possible for them to fly from France anymore because of the high population density. So in Canada, we had the problem was with the other way around, where our system that was flying before year 2000 was obsolete, and we never had the funding to replace it. So we were looking for a flight train or aerostat system that we could fly. So we had the room to fly those balloons, but not the system. So the two countries teamed together, and that's how this collaboration was born. So this means for Canada, this means annual opportunities. So we're not talking about having a single campaign. We're talking about one campaign per year for 10 years. And we'll see later how well this is going. Payload-wise, the maximum CNES can launch right now is 1,100 kilograms. And their flight duration here on the slide says up to 24 hours, but I think in Australia, the flight was 33 hours. So it's slightly up, slightly higher that they're able to do for these flights that are called short duration. But yeah, of course, there's a long duration flight that they're looking into as well, and that other countries are doing. Altitude, between 18 and 40 kilometers. So if a scientist wants to go to an altitude, let's say of 20 kilometers, usually balloon will have to go up, and then they will bring it down. We'll talk about it a bit later. Up there, it's a near space environment. You're not in space yet, but you have some of the elements that you can see and that will allow you to test your instruments or have your experiments. And obviously, one of the big advantages of flying under balloon is you'll be able to recover your payload, improve it if needed, or fly it simply from a different location to get different results the next time. So there's a possibility of reflight. The balloon evolved in the stratosphere, and it's actually the only the only way to get to the stratosphere and to stay there for a long duration of time. All the airplanes will fly lower, and sounding rockets will just go through it in a matter of seconds. So what can we do from the balloon? So remote sensing, of course, climate change, many of the measurements that were done in the past 20, 30 years were done from balloon. Astronomy is done. We've flown 3 telescopes up to now as part of the Stratos program. There are in-situ measurements that are also performed on those balloons. And well, these balloons are also used to test technologies that will later fly on satellites. We're getting here the example of a solar panel where, although you're not technically in space, the environment you see for a solar panel is quite similar, and therefore will help you qualify the panels for future flight on board satellites. Radiation studies are also performed from balloons, and of course, student experiments as well. So CNES has different types of balloon. As part of the Stratos program, what we've dealt with in the past and what is used is the zero pressure balloon. So the BSO is for the French acronym. It's a zero pressure balloon. They also have the near balloons, infrared. But those haven't flown in many years. Spheric pressurized balloon, they have campaigns regularly. I think they have one in 2019. So this is ongoing. We're just not involved yet. And well, they also have the Aero Clipper, I think, that has its own campaign. Not aware exactly of how many they have. So if we go back to the Stratos program, the 2019 is going to be the sixth campaign. So we've had 3 in Timmins and 2 in different locations. So we said earlier that this program means access for Canadian payloads to campaigns on an annual basis. You can see here that every year there was a campaign. The 2 first year were in Timmins. Then we went to Sweden. The next year was Australia. Last year we were back in Timmins, and 2019 will be in Timmins as well. Since it started in 2014, it's 25 large balloons that were launched, 31 Canadian experiments, and you can see the number of student scientists that were involved in all of those campaigns. So if we look at the architecture of the flight train for a zero pressure balloon, we're talking about a system that's approximately the height of the Eiffel Tower. We use here the CN Tower in Toronto, but not as easy as a comparison because it's not quite the same height. But anyway, the full system at 300 meters is what is required to lift a payload of 1.1 ton. If we look at the different parts of that system, at the top of the balloon, you have the exhaust valve, and that's what allows CNES to kind of pilot their balloon. So they could go down to a lower altitude or have a slow descent if required by a scientist, or it could be used as well to get to a different altitude, different lower altitude, to get to a different wind direction, and just basically like a hot air balloon, kind of go different directions by playing with the altitude of the balloon. Other subsystems that are well, obviously at the bottom is where the scientific gondola is located. And you have number 6, which is the avionic gondola that has all the communication means, also has the ballast because, well, we talked about the exhaust valve to go down. By dropping ballast, you could go higher as well. Parachute, I didn't talk about it, was obviously quite important if you want to recover your equipment in a reasonable state. Yeah, gondolas, I'll let Philip go with these ones.
So there are different types of gondolas. A bunch of projects could come up with their own gondolas, but CNES has developed generic platforms, which are aluminum tubular structures. So there's like different classes. So the heavy ones, which can be as heavy as 800 kilograms, and medium size, and also small ones. So it was just to show you like 2 different types of gondolas, even if these ones are quite similar, but they have different purposes.
The balloon, when it's inflated on the ground, we don't realize it, but it's only inflated to somewhere between 5 and 8% of its total volume. And as it goes up, well, pressure will decrease, but the gas will expand and fill up the balloon. So when you get to the ceiling, the picture on the right shows what the balloon looks like, and you can see it's quite different from what it looked like at the beginning when it just got off the ground. And well, we're talking large balloons. So here, and like we had a discussion this morning, myself and Philip, where this 115 meters is not actually right. It's 180 meters. That's the full diameter of the balloon when it gets to the ceiling. And this is so you can actually see it from the ground. We've seen it, yeah. If you have a beautiful blue sky, you'll see it quite clearly with the sun shining on it. Even though it's at 40 kilometers of altitude and 100 kilometers away, you can still see it. Communication system, well, if you have, like with the balloon, it's almost 3 tons of equipment that's flying above your people's head. So obviously that means there are some safety requirements. So all critical subsystems are required to be redundant. And here you have an example. The communication subsystem is obviously one of those critical subsystems. So we're using 2 different means at all times to communicate with the balloon. So there's the S-band downlink that is used to bring back the scientific data as well. And there's an iridium link that will allow to control the balloon even if we were to lose the S-band communication link. Same thing for location. There's 2 means that are used. Well, mainly GPS is the one that gives us the most precise location.
Well, a typical flight timeline, it starts usually early in the morning with a sounding weather balloon. So this gives the opportunity to CNES to optimize their simulation and trajectories. Then the countdown starts. It's usually around 5 to 3 hours before the launch time. CNES brings all their equipment outside. They test one last time each subsystem the valves opening, the pyrotechnic devices, the communication systems. Then we bring the scientific gondola on the launch area, and we unfold the envelope about an hour before launch. Usually this event is critical because once it's unfolded, we cannot really fold it back without damaging it. So that's a kind of a go no go point during the countdown. And the inflation starts. So it takes about 40 to an hour, 40 minutes to an hour to inflate the envelope depending on the size. So CNES has different sizes. 800,000 cubic meters. They also have 400,000 and smaller ones, which is 150 and 100,000 cubic meters. And then we launch the entire system. The flight can last 8 hours till 30 hours. It also depends on the wind and the direction where we're going. If the winds are pretty strong, we'll reach the limit of the S-band communication link faster, so we'll have to terminate the flight sooner. Once we separate the envelope is free falling. It has a beacon on it, so we can actually go recover the entire envelope and system. And the flight train just falls down with parachute. At the beginning, there's a free fall section that lasts few seconds until there's enough air density so the parachutes open. Once we reach the ground, we send a recovery team. Most of the time we use an helicopter because it's quite often in a remote location. Here it's a typical flight profile. So depending on the science that is done by the primary payload, what we see usually it's constant ceiling profiles where you stay during the entire flight at the same altitude. This is mainly used by the astronomy payload because they don't want to change their altitude. They want to stay as high as possible to get away from the atmosphere distortion for their lenses and the measurements they're doing. And there's also the excursion profiles where usually it's the in situ measurement instrument that want to take samples going down till they reach a certain altitude. Let's say they want to look at the ozone around 20 kilometers. We can then stabilize in that region. This is a picture taken on board one of the telescopes we flew in 2015 from University of Toronto. So after the entire night, they've done their mission, then sunrise happened and they captured that beautiful picture. Really briefly on the landing and recovery. So as we said, the envelope is free falling. So we always look at the safe landing zone before terminating the flight. And the flight train, as you see on the right side, comes down under parachute. The distance between the avionic gondola and the scientific gondola is about 75 to 80 meters. And the communication between the scientific gondola and the avionic gondola is done through a Wi-Fi link. So the communication with the ground through the S-band is not done directly with the scientific gondola, but with the avionic gondola, which is above the scientific gondola. Here is the biggest CNES gondola with its thermal blanket sitting straight in the wood.
Talking about remote location. Yeah,
and it's not always the case. Sometimes it's upside down. It could be it's often trees, but usually it's in pretty good shape. And on the left side, there's the helicopter operation, and as you see, there's a part of the envelope in the helicopter net. So a bit more fact about this coming campaign. Like we said earlier, it's going to be in Timmins, Ontario. The campaign time frame is usually mid-August till mid-September, end of September. It's actually
there are still a lot of TBDs on the exact date, and that's simply because CNES hasn't finalized the payload that will be flying, and then therefore doesn't have all the information to look at the trajectories. And the campaigns are targeting the wind turnaround, which happens twice a year, and one of these ranges is from mid-August to mid-September. And depending on the exact type of flight, they may target to have most of the flights before the turnaround or after the turnaround. And that's what's going to decide on the exact date. The wind turnaround when we're talking about the wind turnaround, we're talking about the wind in the high stratosphere. Like on the ground, the winds will change from day to day, from hours to hours sometimes. But at high altitudes, the winds will change directions only twice a year. And for the balloon campaign, we target that moment of the year for the simple reason that before the wind will turn around, we'll do that 180-degree shift, it will slow down. And we target those times of the year because as the wind goes to lower speed, the balloon will travel at a lower speed as well. Therefore, it means it will stay within reach of the S-band antenna for a longer period of time. If we were to launch a balloon, let's say in January from Timmins, because the launch site was selected so we could launch 12 months per year. But the fact is that in the high stratosphere, the winds would be close to 200 kilometers per hour. So if you have an antenna with a 500-kilometer radius, that means you'd be out of sight within 2.5 hours. So that would go for short flights.
So for this year, we are working on a short campaign of 4 flights. I put 2.5 and 1.5 as the European and Canadian content because we will have Canadian payloads on European gondolas, and we are actually borrowing one gondola from CNES that will try to put as much Canadian content on it, but we might also have European payloads on that gondola. It all comes down to the mission compatibility. If 2-3 payloads want to look at pretty much the same things, we'll put them on board the same gondola. We haven't decided yet which gondola will be used. Since Canada and CSA doesn't own its own gondola, we have to borrow it from CNES. So we're working closely together with them in order to come up with a list of payloads and see the compatibility between them. But everything, all this will be decided in December. So we'll come up with a final number of flights, and we'll know which gondola platform we'll use in December, early January. So about the CAN-SBX challenge, we are giving you constraints. So the mass is 12 kilograms, and as an improvement from last year, I would say it was also 12 kilograms, but including the enclosure that we're giving you to put your instrument inside. So this year, I've decided to increase it slightly to 12 kilograms for the payload only. So this does not include the enclosure. As we are facing every day in our work for the satellite world or what we're doing here at CSA, we have to basically meet some requirements. So on your side, the challenge is to have an instrument that is fitting inside a defined volume, which will be explained later. So the power is also limited because we're sharing the power through all the flights. We don't have a renewable power source as Sebastien mentioned earlier, like solar panels. So we're just using batteries. So the power for each payload is limited to 30 watts. And something new for this year, we will give you access to telemetry and telecommand with your payload. Last year, it was standalone payload that had to operate remotely, doing everything. We were turning them on at launch, and we were recovering them at the end. So this year, we'll give you access to telemetry and telecommand. So the bandwidth is limited because of the S-band link, and we have to share also that link with all the other payloads. So the bandwidth for downlink is limited to 50 kilobits per second. It seems really, really low compared to the internet we have at home, but in the stratospheric balloon world, it's not that bad. When you think of, let's say, if we switch to the backup Iridium communication link, it's just few bits that we were allowed to get telemetry. So there's no way we can actually download videos from during the flight. It's mainly to look at the health of your instrument and send few commands. So the enclosure you'll have to fit in, it's a commercial Pelican case. And the reason why we picked one enclosure like this is it avoids you to actually make a bunch of analysis, like finite element analysis, structure, verification to confirm and certify your payload. So since it's enclosed within the payload, we have less justification to do, and it's usually there's so many work on the sensors and the electronics of your instrument that it gives you, there's still like mechanical design, and you have to package everything inside the enclosure, but the final certification through the safety process is slightly reduced. So the enclosure themselves have openings. The picture here shows only one connector. It's because we're gonna have the second one, like I said, for the communication link. There's an interface plate inside the Pelican case that gives you a bolt pattern, and you can actually attach your equipment pretty much everywhere inside the case. So you have to be careful where the connectors are located, just to have enough room inside for the wires. But otherwise, you can actually package your experiments inside the Pelican case as you want. The opening of the case is closed by either a perforated sheet, aluminum sheet, so you can actually have air that goes inside if you want to test reactions or get air samples. It keeps everything contained inside in case something breaks during the flight, but it allows the air to go inside the case. Or there's a Lexan window that allows you to take actually picture or videos from the outside. About the power and communication link. So the power provided is 28 volts DC. So it's unregulated power. It starts at 34 volts when the batteries are fully charged. And as the power is withdrawn and it depletes the batteries, it goes down to 24 volts, which is the safety cutoff power. It's usually we don't go as down because we put enough batteries to power everyone, but your instruments and experiment has to actually work it through the entire range. So don't test only at 28 volts. For the type of current, there's different, depending on the distribution system for power, there's different types of current possible. So we're not sure yet, since the configuration and the type of gondola is not fixed yet, if it's going to be 5 amp or 8 amp. I would say if you're thinking of something, proposing something now, keep in mind that, well, the 5 amp would be would give you more flexibility depending on the gondola that will be picked at the end, but 8 amp line could be also available. The external cables that are interfacing with the Pelican case and the power system are provided by the CSA. For the communication link, as I said earlier, the bandwidth is limited to 50 kilobits seconds. You can actually use the Ethernet protocol. In order to avoid problems, the system usually support the dynamic IP address, but we prefer usually to define static IP address, so it avoids really trouble. And the external cable will be also provided by the CSA. About the environment now. So one of the biggest issue and unknown for you might be the thermal environment. So as we go up, we go through a really cold layer in the tropopause. In Timmins, that layer is usually around minus 70 at night, and closer to minus 50 during the day. As we go up, it warms up again. So the graph here shows the air temperature. It doesn't really show the temperature your instrument would reach under the direct sunlight, but I have information on this later. So here on the ground, you have to basically support the ambient temperature. As we go up, like I said, the temperature will decrease really quickly, but we go through the tropopause within 30 to 60 minutes. It depends on the thickness the tropopause is at that time of the year. The pressure is also reducing, but as we go up, it's pretty slow. So it shouldn't be a problem. The Pelican case has a pressure relief valve, so the pressure is equal on inside and outside. So usually it's not a problem. So at ceiling, the air temperature is around minus 40, minus 30. But when the sun rises, then it warms up things. And also, if your electronic is running, it's gonna warm up the inside the case. During the descent, I would say more stringent thing is really the dynamic pressure that increases really fast. So keep in mind that your instrument has to if you have enclosed or trapped air, things like that, you have to keep this in mind. Here is some example of the surface temperature versus the surface finishes of different types of material and coatings. These are really theoretical values with some assumption written here below. But just to give you an example, if you have an exposed black anodized aluminum plate versus a white painted surface, the difference in temperature at, let's say, on the right-hand side, the environment temperature at -20, the difference is almost 60 degrees different. So an aluminum plate painted white it gives you a 60-degree difference. A bit on the radiation and the outgassing. So radiation, we are exposed to radiation, but for short duration flights, usually the commercial electronic parts are good enough. You shouldn't see major problems through the flight, so no need to really shield or use radiation grade components. Outgassing is really a best practice in choosing materials that usually have low outgassing, but it won't degrade the material enough to influence the structural integrity, let's say, for example. But if you do have optical components, the volatiles could basically, if you have cold surfaces inside, could just stick to a lens and give you blurry images. So if since there's there is some convection, but not much. You don't have a lot of air at ceiling. The volatiles will basically stay close to your instrument, so just keep that in mind. Unballasting, like Sébastien said earlier at the beginning, the avionic gondola has ballast containers, so that's the way to pilot the whole aerostat. If we drop ballast, we go up, so we can actually find a wind direction that will probably bring us further from a populated area or let's say a water body down on the ground. So the ballast container is located on that gondola above the scientific gondola. So CNES is dropping small stainless steel balls. Usually they don't hit the scientific gondolas, but depending on the wind speed and how the gondola is let's say moving below, it could be hit by those stainless steel balls. So by being inside a Pelican case, you'll be protected of that type of ballast. On the mechanical side, the flight itself is pretty gentle. So as it goes up, there's not much acceleration or constraint. Usually the ascent is close to 5 meters per second. The descent is really fast at the beginning after separation, but under parachute, CNES always tries to keep the descent under 7 meters per second. So when we hit the ground, usually it's close to 18, 20, 25 kilometers per hour. So it's not that big, but we never know on what kind of surface we'll land. It could be on rocks, on high grass, in trees. So the acceleration you have to look at is 8 Gs vertical and 2 Gs lateral. The landing, usually for shock, we look at higher impact because we never know on what kind of really ground will land, as I said. But this can be done by calculation. The thing is, at landing, if something would ever break, it's a bit, in a sense, less important that if it would break after separation of the envelope and the parachute opening. The fact that you're enclosed in a Pelican case helps a lot for the certification that nothing will fall off the gondola. There's also some frequencies you have to be compatible with. it's not allowed to emit, let's say, on board the gondola. So we're not interfering with the frequencies and the other communication device from CNES. So here's a list of the frequencies. It happened this year that a team used a router to actually plug several components of their experiment, like the Raspberry Pi with one cameras, and they were using wired connection, but the Wi-Fi was enabled by default. And we found it out during the flight. And since the gondola is about 75 meters below the avionic gondola, the Wi-Fi link is pretty weak, and they both network were competing against each other. So we are now doing some verification towards this. So these are the frequencies used by the CNES system.
I think it's a good time probably for questions.
Yep. So we could, before talking about the safety documentation, open the floor for questions.
Philip, I actually had a question. As you know, last year we had a team that required visibility to the ground, and they were able to work with the CSA team in order to accommodate that. Is that something that we'd be willing to do this year as well, if in fact another team requires visibility to the ground?
Let me just go through here. So yeah, it's we try to, because we don't know what kind of experiment you'll propose. We came up with a Pelican case and 2 openings, but since most of the CNES gondolas don't offer nadir pointing, we worked on a solution with a mirror that will allow this team to actually take pictures of the ground. So yes, it's something we could definitely look into. I would say if it falls under the mass budget given, we can certainly look at this.
Great. Another question that we got online was, let me just see here. So does the gondola record and timestamp altitude data?
It's on some gondolas there is some computers on board. Depending on which gondola we're flying and which subsystems are available, it is possible to get real time, time actually, and GPS data. But if it's not available real time, it can actually be retrieved after the flight. So, if your payload is synced with the let's say UTC time, after flight we can actually give you the location and the flight path. So it's something that can be given after the flight.
Perfect. Thank you.
So you mentioned that we can have something sticking out the size of our payload. We were thinking of doing something along the lines of a radiometer. How much kind of diameter could we have on that?
Well, the diameter, it depends on it. Well, if you have something that is really sticking out far, we would have to really look at it a bit deeper, because during launch, the CNES operation team has to lift the gondola, and if there's something protruding like a boom outside of the gondola, we have to really look at this with them. Otherwise, the only constraint is the mechanical load. So if it's something that is pretty light on a tube, we would just have to you would just have to provide the calculation that the tube won't break under the separation load.
Do you have a size in mind?
We were thinking of doing an radiometer in the L band, which we would probably want. I mean, the bigger the antenna, the better. But we were looking around dish sizes of 1 meter in diameter. But you know, we need to do a trade study and think about if we can use higher frequencies, potentially. Something maybe at 8 gigahertz would be a smaller antenna, but all of the components would be more expensive, for example.
That's a good question.
But I'd go strictly on a mechanical point of view. A meter, I don't think would be. It would be hard to get to fit it on a gondola.
Yeah.
Well, at least within this project, it had to be a flight that's.
Yeah, I think it makes sense if you plan to propose a project. I would say if you could just expand a little bit about what is the flexibility, what is the possible range for you, and then we could probably spend some time to discuss about what's feasible and not.
Yeah, because depending on the complexity, it might qualify itself as a separate payload that would require a bit more room and because I think the whole intent of this challenge was to give access to a flight, but within a certain volume, just so we can actually put you on board several gondolas without too many constraints. But yeah, if you can provide us a bit more detail, like Sébastien said, a meter might be a bit more stringent on.
Does it really have to be a dish, or?
It needs to be as directional as possible. So, it's like some satellites use antenna arrays, and the individual antennas in that case don't need to be very large, but they do need to be spaced quite far apart. Okay. So that's something potentially we could think about. But I think for us, maybe just picking a higher frequency and going with a much smaller antenna is maybe a better plan of action.
Good. Yeah. Sounds good.
Yeah, for sure. So, like the guys said, when you submit your proposal, just make sure to kind of give an outline and maybe a couple of different approaches that you think that you'd be able to take, and then like we did last year, like the CSA is always willing to work with the teams, so I'm sure there's some plan of action that we can achieve.
Yeah, absolutely. Yeah, we'll submit our proposal and we can discuss it more after that.
Great.
But is the 30 watts would be sufficient to have your because that's another limitation. It's also the power. So if you're looking at a really powerful antenna, or it might also be the another constraint.
So it's a passive microwave sensing. So we're not so we don't.
Okay, good. Excellent. Yep.
Okay.
Perfect. I think, are there any other questions?
I think we're good. Thank you.
I think we're good. Yeah. Oh, I do. Well, I guess it's sort of it, but just the thermal blanket. I assume we would have to make some sort of reservations in terms of getting a nadar pointing antenna through this thermal blanket.
Well, the thermal blanket you've seen on the gondola that was on the recovery picture is really specific to that gondola. So the plan is more towards using the 400 kilograms gondolas that we've seen earlier in the presentation. So these ones don't have thermal blankets. It's really just a tubular structure, and each payload usually provide its own thermal protection.
Okay. All right, awesome. Thank you so much. That's all our questions, I think.
Excellent. Do you guys want to pick up at the safety documentation
Yep.
where we were? Excellent. Thank you.
So, so in addition of the this challenge, well, you'll have to provide. We want to make it like a real engineering project. So there's some reviews and documentation to provide, as well as progress report. But in order to get certification, there's some safety documentation to deliver. So the team that will be chosen will have to fill a more detailed application form, which basically gives the flight profile the team would like to get, the dimensions. We know them, but it's mainly the hazards. Do you have hot surfaces? Are you using chemicals inside the enclosures? Are you using batteries or let's say pyrotechnic devices? So you have to identify and declare those hazards, and also provide the hazard sheet. Later in the project, the team will have to come up with a safety data pack, which is basically a kind of design document that explains the payload. But also it's where you guys are describing. There are few requirements to meet towards the safety of the flight. So it's where you justify how you actually meet those requirements. And at last, sometimes it's not really complicated, but for payloads that have optical lenses or power or hot surface, it's good to put together a recovery procedure that actually shows the recovery team what they should know about your payload in order to protect it and also protect themselves. So like we saw earlier, this is the MIST team from University of Alberta who flew optical payload last year. So we put a small baffle on the side to allow them to take measurements. And the second payload was on another gondola. It was also a team of University of Alberta. The Pelican case, sorry, is that one has two openings on both sides with the perforated mesh. So they wanted to test the reaction of a calcite powder with the stratospheric air. So we don't see the openings, but it was sit close to the edge of the gondola, so the air could go inside the case. So the picture on the right is the gondola on the launch pad with the last minute check. So a little bit on the Timmins stratospheric balloon base. So the Timmins launch base is considered as a CSA lab. Unfortunately, we have to perform for, let's say, every employees at CSA, but also people who are getting access to our lab. That kind of security check has to be performed, because once you come to the Timmins launch base, we give you an access card, and you basically have 24/7 access. You can test at night if you need to look at, let's say, stars or do whatever you want. You have access to the payload integration at all times. So in order to have access to the since it's a fenced area around the base, you need access to the main gate and also the buildings on site. The base is located at the Timmins Airport. So it's really easy to go to Timmins. There's, I think, 6 or 8 flights per day from Toronto. So there is a security check. The base itself, like I said, it's close to it's on the airport area. The launch area is on the upper section. So there's an arrow here to 2 launch areas. So it's fenced. There's many buildings. So the green ones are the ones that the scientists and the payload teams have access to. And yeah, so just to give you an overview of the launch base in Timmins. To get access to the launch area, usually the student teams are pretty big. So and that's a good thing because we want to train as many people as we can. So we, for the launch itself, when you guys need really to remove an optical cover or turn one switch on, we give you access 30 minutes before launch to your payload. After this, we have to really go back close to the fence and look at the launch. In order to not having everyone around the gondola, we give access only to 1 or 2 persons per team. But we bring you guys, we take the whole team during the countdown, and we basically go through the entire system. We walk on the launch area, so I explain usually how what are the subsystems, and you will have a look. It's just that 2 persons will work closer to your payload till the end of the countdown. In order to have access, we need high visibility clothes. We have few vests like this, but we suggest that you bring your own one, so we have enough. And like I said, it's only if you're escorted that you can go on that area, except the 2 persons that will have access. As a service, so the payload integration building is a huge area with 5 integration bays. Usually we have a lot of scientists inside, so we also have science offices, which are ATCO trailers beside the integration bay. We have a cafeteria for you guys with fully equipped kitchen. We also have a barbecue grill, so you can actually cook your own meals on the base and work late if you ever need to do testing or integrate your payload. As for the last slide, I think the Timmins launch base, CSA has some tools and equipment over there, but we suggest strongly that you guys bring everything you think you'll need. There is some stores in the Timmins City. Timmins City is located 10 kilometers from the airport, so you have access to Home Depot, Best Buy, a bunch of other stores. You can also order things on DigiKey if needed, but if you need to debug, repair your instrument, you should bring your tools and also bring extension cords or whatever you think you'll need to perform your mission. During a flight, usually since the payload is taking out to the launch area and we launch it, we transform usually with tables, and we use space as a mission center. So there is some TV screens inside the integration hall, and we actually broadcast the CNES telemetry. So we show the flight profile, the trajectories, and some telemetry about the location, the speed. So you'll have access to this. And this is where we're actually plugged in the CNES communication system, and you get your telemetry from there. So that concludes the presentation. So we'll open the floor for a question.
Yeah, I have a quick question here. So I know that last year, and I know it might be a bit early to know this for this year, but last year the CSA and CNES presidents both made an appearance to the base. Do you anticipate that happening again?
Well, like you said, it's pretty early to say.
Mm-hmm.
We're quite lucky to have both presidents there last year. We'd be really lucky if we get them 2 years in a row. Let's just put it this way.
Fair enough.
Yeah, well, I don't think it will happen. We don't know yet, but as a baseline, since they came last year, I don't think they're planning to come back, but we never know. Especially if there's like a lot of students on site, they might want to come. Especially our president.
Yeah, we haven't gotten any questions online, so I think that's it.
Excellent. Well, in any case, if you guys have questions afterwards, you can contact Robert and we'll answer them. We hope you'll send a lot of proposals, and we'll have to review them. And I'm concluding by wishing you good luck.
Excellent. Thank you.
Thanks. Awesome. Thank you so much.
Thank you.
Thank you.
Just so you know, Robert, I'll send you the presentation.
Excellent. Yes, I was just going to ask you that.
Yeah, and I'm pretty sure people will want to have access to it, since I have a lot of information. I'll send it to you shortly.
Perfect. Thank you.
Okay. Thank you very much.
Thank you. Take care.
Thank you. Bye.
Good. Well done.